Okay, welcome back to the class. I wish you had a good 추석. And we start with a quiz. 자, 어서 들어오세요. 오케이, 들어올 만큼 들어온 것 같다. 보자. 어떻게 25명이지? 내 수업에 24명인데 조교님도 안 들어오셨는데 두 번 들어온 사람이 있나? 여하튼 일단 수업 시작하겠습니다. 야, 이건 너무 심한 거 아니야? 우리 1학년도 없는데 여기 최소한 2학년인데. 나중에 나 보면 이거 누가 무슨 답했는지 다 확인 가능해. 이러지 말자. 수업 시간에 뭐 다 외우라는 건 아니지만 기본적인 거는 알고 있으면 좋지 않아? Carbon-carbon single bond is approximately 1.5 angstrom, right? 1.5 angstrom is equivalent to 0.5 nanometer. Nanometer is 10 to the minus 9, right? And picometer is 10 to the minus 12. So 120 picometer is equivalent to 0.15 nanometer, right? So carbon-carbon single bond 1.5 angstrom. Carbon-carbon double bond is 1.3 angstrom, and 120 is approximately triple bond, right? So that much, let's remember. Okay, move on. Okay. Visible light range is approximately between 400 to 700 nanometer. Above 700, actually, I don't think any of us can look at as a color. So that's too far, a little far. That's almost near to the near IR range. So real clear, the red light, especially for the laser pointer, the red color is about 650 nanometer. Okay, 400 is about the violet. 520 is a green color. So that means the blue color is about 470. And 490 is this color, orange color, like this. Okay, so red color is approximately 650. Okay, move on. Okay, not bad. So standard is here, visible light. So longer one, near IR, far IR, right? And to this way, near UV, far UV. Far UV is the shortest. Okay, good. Okay. Yeah, the answer would be either A or C, right? So standard is here, visible light again, and then near UV and far UV or deep UV. And if you give the code, then you may start here too. So near one is A, B, C, moving out, right? We don't give ABC to the IR, but still if you give anything here, near IR 1, near IR 2, near IR 3, okay? Always the standard is our view. Visible light is the standard starting point, okay? Okay, better than I expected. So usually I don't require you to remember too many things. Minimum, for the exam, you may need to study thoroughly, but at least for each class, I expect you guys at least to think together. Then these quiz questions are just check whether you're thinking together with me. But this one is requiring a little memorizing. But anyway, 171 is a single double bond, one double bond. 217, two double bond. 258, this is a triple double bond. Okay, so this is something we are going to handle today. So I wanted to remind you approximately this range. All of them is shorter than 800 nanometer, the 300 nanometer. It's quite short wavelengths. It's a deep UV, UVC range, or the far UV range. This is very high energy other light. Again, the borderline of a visible light, 400 nanometer. Okay. Okay, very good. What is the correct term for this, the blue one? Diane?
네, 스펙트로메트리라고
That's
알고 있습니다.
spectrometry. Okay. So spectroscopy means why this is wrong, Diane?
그 한국어로 답변 드려도 괜찮을까요?
Okay.
그 매스 스펙트로메트리 같은 경우에는 빛을 이용해서 직접 관찰하는 것이 아니기 때문에 스펙트로스코피보다는 스펙트로메트리가 맞은 표현이라고 알고 있습니다.
Okay, great. Scopy means seeing, vision. Okay. Scopy should require any kind of electromagnetic wave. Visible light, UV, IR, microwave, radio wave, X-ray, gamma ray, any kind of electromagnetic wave is involved. Then we call them spectroscopy. Mass spec does not need any of those light source. It just requires maybe magnetic field, but that's not light. Okay? All others, UV, IR, NMR, they use light. So that's why we call them spectroscopy. Yeah, this is surprising to see the transition state is the highest, the number of answers. Okay, last time we learned about the kinetic control and thermodynamic control, right? Kinetic control and thermodynamic control. Kinetic control is related to activation barrier. If it has a low activation barrier, it can go there faster than the other one. But that does not mean that the product is the most stable. most stable one is a global minimum. Okay, it just go over the first lowest activation barrier one and then stay there. This is a local minimum. Global minimum means most stable among all possible products. That's a global the minimum. That means thermodynamic product is global minimum product. Okay, so that is also same word as the most stable state. Now, transition state. If I said intermediate, that is maybe close to this local minimum. So here is the product. You can see my cursor, right? Okay, so now reaction goes over here, and then they stay short time here, and then they go over further. Then this short-term intermediate state is a locally minimized state here. Then material can stay there. But transient state is different. Transient state is not here, that is on top on here. This is transient state. Transient state, you cannot isolate the product. That's just the imaginary state. Nobody has seen it. That's just we hypothesize. There may be some state which passes this top area. This is the energetically unstable, right? Material does not stay there. They move either go back or to go forward. So local minimum is more closer to at the intermediate state. Intermediate state, you can detect, you can isolate. But transient state, you never. That is just imaginary. Okay, that's a big difference. Okay, move on. I gave you one question about the kinetic control. Next question is about thermodynamic control. Okay, let's review about this thermodynamic, the first law and second law. You guys have learned this in the general chemistry or maybe the physics. So let's review this. First law. What is the first law? Let's ask Yoon-kyung. What is thermodynamic first law? 윤경아, 조윤경. 윤경이 안 들리는 척한다. 마이크 안 켜고 마스크 쓰고. 진짜 안 들리나? 그럼 안 들리는 척하는 게 내가 쏘갔다고 치고. 현아, what is the first law of thermodynamics?
고립계의 에너지가 일정해서 에너지는 생성이나 소멸되는 것이 아니라 전환되는 것이다라고 알고 있습니다.
Total energy is not changing. Okay, that is the thermodynamic first law. What is the second law? Second law, let's ask 영수. 영수 is not here today.
네, 교수님.
Okay.
엔트로피로 봤을 때 어떤 열적으로 고립된 계에서 엔트로피는 항상 증가되는 방향으로 이동된다라고 알고 있습니다.
고립된 계라고 얘기를 했는데, 오케이. 고립된 계이거나 토탈 시스템이거나 거기서 엔트로피가 증가되는 방향으로만 일이 진행된다 하는 것이 thermodynamic second law가 맞습니다. 그죠? 그런데 세 번째 거 보면 엔트로피가 맥시마이즈 되는 쪽으로 가는 건 맞는데 내가 여기다가 함정을 약간 파놨어요. 프로덕트라고 써놨어. 프로덕트만 보면 안 되고 전체 시스템에 대해서 혹은 그 전체가 완전히 고립되어 있는 계이거나 그 계 전체에서 봤을 때는 엔트로피가 맥시마이즈 되는 게 맞아요. 프로덕트만 보면 안 돼. 생겨나는 부산물도 같이 봐야 돼. 자, 마지막 거 많이 선택을 했는데 깁스 프리 에너지는 맥시마이즈 되는 쪽으로 가나요? 반대죠. 깁스 프리 에너지는 엔트로피가 증가하는 방향, 여기는 사실 엔탈피까지 포함된 것이 깁스 프리 에너지이기 때문에 깁스 프리 에너지는 우리가 쓸 수 있는 좋은 에너지라는 뜻이고 깁스 프리 에너지는 미니마이즈 되는 쪽으로 가는 거죠. 오케이? 자, 깁스 프리 에너지를 계산해서 끄집어낼 때 깁스 프리 에너지를 계산할 때도 전체 시스템에 있어서의 엔트로피를 가지고 유도했습니다. 엔트로피는 증가하는 방향으로, 토탈 엔트로피는 깁스 프리 에너지는 줄어드는 방향으로 반응이 진행됩니다. 세상의 모든 일들은 우리가 주로 다루고 있는 것은 분자를 다루고 있고 분자 속에서도 전자의 이동을 다루고 있는데 전자의 운동을 다루고 있는데 여기서 전자가 어느 쪽으로 이동할 건지에 대한 큰 방향성은 깁스 프리 에너지가 결정하고 그거는 엔트로피가 증가한다는 것과 같은 얘기고 그거는 세모다이내믹 세컨드 로에서 제2법칙에서 다루고 있는 이야기입니다. 그렇기 때문에 세모다이내믹 컨트롤이라고 부를 때는 세상의 모든 것들은 충분한 시간을 주면 모든 게 가장 스테이블한 글로벌 미니멈으로 가고 엔트로피는 증가하는 방향으로 가고 깁스 프리 에너지는 줄어드는 쪽으로 간다 하는 이야기입니다. 오케이? 영어로 얘기하면 내가 영어로 잘 표현을 못할까 봐 여러분 영어를 다 잘 알아듣겠지만 그 부분은 한글로 표현했습니다. 넘어갑니다. 생각보다 잘 맞췄네. Okay, Schrödinger equation, the answer of the Schrödinger equation, after we solve the equation, we get wave function. And also we get the energy level. Energy level is the eigenvalue of a Schrödinger equation. And wave function is the information about the electron distribution or the electron shape, or we call probability of those existence of electron, right? Molecular shape, we cannot get it directly from Schrödinger equation. Always we use approximation. So that was the point I wanted to tell you. Okay, let's start today's lecture then. Okay. Okay, this one we pass. So now this is the second week and we are studying this chapter 15. Any question for the quiz? Okay, if not, we move to today's topic. Okay, today we are going to study about the benzene and aromaticity. This is the shape of benzene. Benzene is a very unique molecule. Why this is unique? Anybody can tell? Dayan, why benzene is unique?
정확하게는 모르지만 벤젠은 고리 구조랑 컨주게이션 된 구조를 같이 가지고 있어서 독특한 아로마틱한 성질이 있다고 알고 있습니다.
Okay, what is aromatic? Aromatic 성질? In Korean, what do you call it?
방향조,
방향성, 방향. What is 방향? Is that direction?
예, kind of smell?
Kind of smell. Great. 방향 is 방은 내보낸다는 뜻이고 향은 향기죠. 방향이라고 하는 것은 냄새를 풍긴다 이런 뜻입니다. 남쪽 방향, 북쪽 방향의 방향이 아니라 아로마티스트를 가진다. In the beginning, benzene was really smelly. And many of those the benzene-related compounds are smelly. That's why the name was given to the aromaticity, 방향성, smelly property. But actually, the aromaticity does not mean smell. It means something else. Anybody can tell? Okay, 꽤 복잡한 얘기니까 자 한번 배워봅시다. 아로마티스가 무슨 얘기인지. First of all, naming. So the mother structure of this molecule is benzene. That's why if you have this kind of a structure, bromobenzene, nitrobenzene, propylbenzene, makes sense, right? But benzene-related compounds, there are many different structures, so they have their own non-systematic name, the IUPAC name. So they have, if you have one methyl, you should call methylbenzene, but it has its own name, toluene. If you have a hydroxyl benzene, you can call it that way too, but they have its own name, phenol. Aminobenzene is an aniline. This is a little more complicated, acetophenone. Let's skip. Now, the other way, not just calling the basic structure, now utilizing this one as an adjective, benzaldehyde. Now, benz is the adjective here. Oops, not there yet. Okay, color. Benz up to here. This is adjective, benzaldehyde. Sometimes it's further changing benzoic acid, acetic acid, benzoic acid. Now, if you have one methyl toluene, 2-methyl xylene. If you pronounce the xylene, that's Japanese, not English. So we use the English textbook, so let's pronounce as the English way. Xylene, and then depending on those positions, we have ortho, meta, para, kind of things, right? And then this is a double bond connected together. This one is a styrene. So not many molecules, but these molecules are very common we encounter in organic chemistry. So even though this is not systematic name, it's good to know these names. Okay, this much I require you to make yourself familiar with these materials. Okay, acetophenone will not cover. So this one 빼줄 테니까 나머지는 이름 알아두면 좋겠습니다. It's very common structures. And if the ring is fused into two, we call it naphthalene. I'm not sure, we still use naphthalene at home. When I was young, we used naphthalene in Ojang, and we kept that smelly small balls. It's like a mint hyang at the smell bowl, and it keeps the bugs out, right? So this is naphthalene. One more structure, anthracene. Now here, these two connected one, I may want to call it bibenzene, but they gave the name as a biphenyl. Now there's a little further the description of this structure. Now if you look at here, this motif, the left side of this motif and this one. The mother compound was a benzene. Maybe we wanted to call this a benzyl. But by funny way, benzyl is this one. This one is a benzyl. And by convention, we call this motif as a phenyl. You have that one in your notebook, I think. So this one is called as a phenyl. Then how do you call this molecule? Two ways. Maybe you can call this is a 7 carbon. So heptyl benzene. You need to pointing out this position. But the other way is you call this one as, use this as a main chain and call this one as a phenylheptane. And position is a 2, right? So maybe you can call this 2-phenylheptane. If you put this 2 into here, inside, in between here, that's still okay. Phenyl-2-heptane is also acceptable. Okay, at least by looking at those structure, you can give a name, and by reading that name, if you can draw those mother structure, that's fine. Now, key here is this motif is called as a phenyl. Benzyl is one more CH2. This is a benzyl. Okay, this much. This is quite important. So this much I wish you guys to know and remember. Next, position of different materials. There is standard position. If you have the first position like this, that's ortho. Next one, meta. The next one is a para. Para is the opposite direction, right? So we call this is a para. Then you can imagine ortho, meta like this. Okay. Ortho is the word from the orthodox. It's the right thing. The original one is ortho. Meta is the next, right? Metaphysics. Para is a little far. That's a para. So also metapara. Original meaning is there, but anyway, this is a chemical terms now, settle down. Around this benzene ring, also position, meta position, para position. Okay, not difficult, right? Now we think about the stability of these two molecules. This is a cyclohexane. And this one, by removing 2 hydrogen, we made it into a cyclohexene. 1 double bond there. Which molecule is more stable? 상학. Which molecule is more stable? cyclohexene or cyclohexane?
사이클로헥신이 더 안정한 것 같습니다.
Which one?
사이클로헥신.
You mean this one? 발음 이걸로
네.
한 거 맞아? 헥신, okay.
네,
This one we call 한국말로 하면 헥산이고 헥센인데 in English it pronounces hexane, hexene. So 상학 said this one is more stable. Do you agree? Every bond is saturated and one bond is unsaturated. Which one may have more energy, do you think? One molecule is composed of all sigma bond, okay, very tightly connected together. There is pi bond here, which has more mobility moving around in this box, right? Which one may have more energy? We can assume this pi bond has more mobility, more dynamics, more energy. That means that this molecule is less stable. This molecule is more stable. Okay. This energy is depending on how you define go to this direction or this direction. Okay. This energy is said as a hydrogenation. Means moving from here to here. This is a Gibbs free energy. It's a negative value. That means that this is more stable. Okay. So one double bond is approximately 120 kilojoule. 2 double bond, maybe double amount of that. Yeah, similar to that, right? Triple double bond, we can expect if it's a triple double bond, maybe this one should have this much of energy. But very interestingly, benzene's real energy state is here. That means we, by calculation, by number of that double bond character, we expect benzene is this much unstable or more energetic. But surprisingly, 160 kilojoule discounted energy level it does have. Benzene is much more stable than we expected. Okay, by those conjugation and absorption energy. So this one we have seen today, right? And 3 triple bond, 3 double bond. We expect that this one has a 260 nanometer, but benzene's the absorption energy surprisingly low. Means this is around here, even in between 1 double bond and two double bond range. Maybe we can think benzene's this triple bond is not expanded box like this. This box size like this size, but benzene is much smaller box and more tight small boxes. That's why jumping from this box comparing to this size of a box, it does require much high energy to jump. When we had much bigger box, particular box model, they becomes much longer and longer wavelengths, right? Longer wavelengths means lower energy. They can jump much easier with a lower energy. Benzene requires much higher energy. That means benzene is very stable as it is. And also the particle box size is very small. We draw those double bond this way, but actually this the double bond we can draw this way, and then we can make the other form of this molecule. What do you call this relationship between these two molecules? Is that equilibrium? Is that isomer? Suyeon, would you like to call this isomer?
resonance loss.
This is called as a resonance. Resonance is described this notation. Equilibrium is this notation. If it is a fully isomer, stable isomer, we just call the put almost a reaction. One move from one to the other. Okay. Now these electrons are moving quite fast. The resonance, there is no atomic changes, means nucleus is not moving. Only electron is moving. That's a resonance. Okay. Even proton is moving. That's not resonance. Only electron is a moving structure. That's resonance. And this movement of electron looks like it's quite fast. And then seems like they have a phenomena of these electrons are, these 5 electrons, inside this cyclic box, they look like they circulate like this. It looks like they have a ring, the current moving of electron along this ring. That's why this current we call ring current. Now, this spinning effect or this orbital effect, rotation effect, is observed in many materials in nature. Let's assume hydrogen atom. Hydrogen atom has a 1 nucleus and 1 electron. Electron has a spin effect. Spin means 자전. It's moving. It looks like it has effect of this rotating effect, self-rotating. That's a 자전, right? That's a spinning effect. Nucleus also has a spinning effect, some nucleus. And if the charged particle spin, they behave like small magnetic material. If they spin, then they generate this kind of a magnetic field. They behave like a small magnet. If they are just a random state, we cannot recognize which one is which. It's averaged out. But if you apply magnetic field from outside, this is the external magnetic field applied to the molecules from outside, then they align along these magnetic field directions. Some of them is following same direction. Some of them goes to the opposite direction, and they are separated by different energy. Without magnetic field outside, they are randomized, so we cannot distinguish them. But if you start to apply this magnetic field from outside, they align. Half of them, approximately half of them goes this way. Slightly lower population, they moved this way, and there is a 2 energy state. When they have different energy state, it's possible that they can observe energy. In this case, also the energy can be given by electromagnetic wave. And this energy state induced by nucleus, that energy state is very small. And then electron energy state in a particle in a box model, when we talked about the electron transition from bottom to up here, that was a visible light or UV light, right? It was a very big energy level. And then vibrational mode inside there, those are smaller, those are IR range, IR spectroscopy range light. In this energy state, it's very, very small, much, much smaller than this. So IR, UV, now this one is near to the microwave. Microwave wavelength is, visible light wavelength was a 400 nanometer. IR is maybe 100 times longer than that. It's a micrometer. And microwave is almost 1 meter. Now, if it is a 1 meter, I wanted to give you the surprise problem. So I didn't give this page to your notebook. If 1 meter microwave is used for excitation in NMR, what can be the frequency of that microwave? Can you calculate quickly? 조교님, 누가 좋은 답을 주는지 잘 체크해 주세요. 계산 한번 해볼까요? 힌트 드릴까요? 힌트. 프리퀀시와 파장을 곱하면 속도가 나오죠. 속도를 어떻게 하나요? 여기도 힌트 또 줬죠. 마이크로웨이브도 빛의 일종이고 파장은 다 다르지만 모든 마이크로 일렉트로마그네틱 웨이브는 같은 속도를 갖죠. 무슨 속도? 빛의 속도. 자, 모든 힌트는 주어졌습니다. 계산 한번 해볼까요? 이 프리퀀시는 얼마일까요? 여러분들 라디오를 듣는지 모르겠는데 AM, FM 뭐 이런 거 있습니다. FM이 조금 더 파장이 짧고요. AM이 파장이 좀 더 깁니다. AM은 킬로헤르츠 레인지고 FM은 메가헤르츠 레인지로 갑니다. 거기서 사용되는 헤르츠도 일렉트로마그네틱 웨이브의 파장을 뜻하는 거죠. 자, 그러면 NMR에서 사용하는 1m짜리 마이크로웨이브를 사용하는 NMR은 주파수로 따지면 얼마나 될까요?
300MHz.
곱하기
오,
10의
지원이가 가장 빨랐던 것 같네. 두 번째 답한 게 누구지? 유진인가? 현아인가? 지원이 잠깐 기다려주고. 또 답한 사람 누구였어? 유진이 뭐라고 그랬지?
3 곱하기 10의 8승 헤르츠라고 했습니다.
3 곱하기 10의 8승 헤르츠. 자, 답도 맞고요. 그런데 그렇게 표현하는 거 별로 안 좋아해. 그거를 10의 8승을 표현하기 위해서 우리가 쓰는 접두사들이 있죠. 킬로 쓰면 10의 3승. 10의 6승은 얼마죠? 뭐라고 쓰지?
메가.
10의 6승은 메가라고 쓰죠. 3 곱하기 10의 8승이니까 답은 맞아요. 300MHz. 자, 유진이랑 지원이가 거의 동시에 각 좋은 답을 줬습니다. 300MHz. 자, 우리 NMR 얘기 들을 때 300메가 이런 얘기 하죠. 이 300메가는 앞에서 봤던 이 에너지에서 두 개가 갈라진 이 에너지 상태에서 요만큼의 에너지 갭. 프로톤 기준으로 했을 때 프로톤이 흡수하는 에너지가 일렉트로마그네틱 웨이브의 파장이 주파수가 300MHz에 해당하는 마이크로웨이브를 흡수한다라는 뜻입니다. 주파수는 크면 클수록 에너지가 크지나요? 작아지나요? 주파수는 클수록 에너지가 큽니다. 그렇죠? 속도가 고정되어 있기 때문에 파장은 얘가 반비례하니까 파장은 짧으면 짧을수록 에너지가 커지고 주파수는 커지면 커질수록 에너지가 커집니다. 오케이? 그러면 앞에 있는 이 상태를 보면 프로톤이 존재했고 there was one proton. If they observe this much of energy, then we can see something maybe. Then NMR is a absorption spectroscopy. We learned so far UV spectroscopy as absorption, right? IR was an absorption spectroscopy. NMR is an absorption spectroscopy. No. NMR, after it is observed, and then it is started to relax, to coming back, and we monitor this energy. That's why NMR is kind of emission spectroscopy. Okay. Now, this whole range of energy, if everything is the same, then we may see only one signal. If all the proton is in the same environment, we see exactly the same signal, but actually it's not. This is one of the very early the proton NMR spectrum of ethanol. This NMR was taken in 1950. Looks like a terrible spectrum, right? This spectrum made the Nobel Prize because this signal is that energy, the energy measured by those absorption and re-emission or relaxation of that observed the light. That light approximately, let's say 1 meter. Actually, this is much longer one. In this case, they didn't have 300 megahertz. This may be 10 megahertz or 20 megahertz. Very low, the energy level. But important thing is, among those protons, this technique can recognize those difference by looking at those size. We can assume this is 3 signal here, 2 signal here, 1 signal here. They can distinguish different proton. How? depending on their environment. Now, this proton has near to electronegative atom. So this electron is withdrawn by this oxygen. That's why this has a low electron environment. Relatively, this has a higher environment, and this is in the middle. That's why they shows a different signal. This means using NMR, it's possible to discriminate different environment proton. That is the main discovery by this NMR. And the unit here. Anybody remember the unit of NMR? Nobody? In NMR spectrum, what do you call this unit from here to here? TMS is 0. What is the unit?
Part per million.
Part per million, great. ppm. UV spectrum, we use nanometer as a unit. IR, we use reciprocal centimeter. Centimeter is wavelength. Reciprocal means that this is a frequency. Okay. It's by convention. In UV spectrum, we use the wavelength as a unit. IR, we use the frequency as unit. This one is called as a wave number, but the meaning of this other unit is a frequency. And ppm. What is ppm? Why ppm? ppm is like a percent, right? Percent is 1 per the 100 is a percent. ppm is 1 per million. That's a ppm. That means there's some standard, and then there is a small difference from the standard, right? What is the standard? That standard is the average value of that energy absorption here, 300 megahertz. 300 megahertz, this is the standard. Among this 300 megahertz, that means maybe in the middle here, this is average 300 megahertz. From this average, how many ppm is shifted to which direction? That's the ppm. That means 300 megahertz in the middle, then unit up to here. If it is 1 ppm, that means this is only 3 hertz difference, right? That's a ppm. So that means NMR is measuring very small changes from given magnetic field from outside. If that 300 megahertz is shifting, magnetic field is changing, it's very difficult to monitor these small changes. That's why if you take NMR, by giving this magnetic field, and then you need to monitor this shifting of this magnetic field. Magnetic field is not stable. They can be slightly moving like this. Then, when recently we got the movie Top Gun, right? The jet fighter, if they find the enemy enemy plane, usually they follow those enemy plane, and there's a locking to monitor that enemy plane, and then you can start to shoot the missile. That locking is fix that object and then follow their movement. Then you can reduce their errors. That's locking. Similar things we do in NMR. We measure those molecules, then usually we give the locking signal here. Then NMR sample is still there, but magnetic field is slightly shifting. We follow them. And then measuring those relative amount of a ppm unit. Okay, that's quite an amazing technique. And then using that, now we can look at those ranges. So usually we give those value 0 to 10 in proton NMR, 0 to 10 ppm range. It's a very sensitive machine. But in the beginning, let's just say, giving those direction this way or this way, that's arbitrary, right? So for some time, there was the other unit, 1 to 10, this direction. In the beginning of NMR, the history, then they call this unit as a sigma value. Sigma value wise 1 to 10 is exactly opposite to ppm 0 to 10 this way. But now this unit disappeared, and then we use always this ppm. And then just arbitrary reference, we use a TMS, tetramethylsilane, as a reference. And this one, silane is electropositive element. That's why it provides more electrons. More electron around, they have low ppm. Low electron density, they go to the high ppm. More electron, those electron is shielding that atom. We call this area is shielded. This area is de-shielded. Okay. Now, following that, now if you give more, if you apply higher magnetic field, then the energy gap is becoming bigger. Now we heard 300 megahertz here. Now, if we have a 600 megahertz, then the wavelengths of that magnetic field, magnetic wave, electromagnetic wave is half, and frequency is double. Okay. Then if you use the 300 or the 600 megahertz, same ethanol, now we can get this kind of a quality of animal. You guys just learned the last chapter as an animal. I want you to review briefly. Now with the high resolution animal, now we can see three different kinds of proton, and again, coupling pattern, and then we can get a lot more information from here. Okay. So to summarize this animal, from 0 to around the 10 range. If it is just a simple alkyl, it's around the 1 area. If there is any heteroatom attached, alcohol or the oxygen or halide, that's about 3 to 4 range. Double bond, it's about 5 to 6 range. At least this much is good to memorize. Then you can look up to those NMR spectrum. Okay. Again, simple alkyl 1 to 2. Any heteroatom 3 point something. And double bond 5 something. Now benzene has a little bigger the shift, around 7 to 8. So this proton here directly attached to the benzene ring has about 7 to 8, and it has a more de-shielded effect. And that explanation is like this. Seems like that electron around this benzene ring, they have a circuit, making this kind of ring current. Spinning can generate a magnetic field. This kind of orbital, the current, this is also generate a magnetic field. And this magnetic field is following that Faraday rule. Looks like this kind of magnetic field is generated. This induced magnetic field is always resisting to external magnetic field to reduce it. That effect happens inside here. External magnetic field is applied this way. If you have any kind of electron cloud, then they generate opposite direction of magnetic field. So this is happening here. This is induced magnetic field. But as a result, if this happens this way, then outside it has this direction. This direction is the same direction with the external magnetic field. That means environment-wise, this proton is experiencing even bigger magnetic field here. Bigger magnetic field, what is the result? If you have a bigger magnetic field, then the absorption energy becomes even bigger, right? It's a very small difference, but if this area is stronger magnetic field, this plus this local one, and then this one is further going to the downfield. More de-shielded effect, they call. Because of this effect, around this benzene ring, this one has a little longer, the more the downfield shifted than alkyl. Alkane has about a 5 point something, 5 to 6. Now this aromatic ring, they have about a 7 to 8 range. Even this position, benzylic position, this has a partial effect of this ring current And usually this position should be, IKL should be 1 point something, right? But this one is just shifted a little, downfield shifted. And this one also gives about 2 to 3 range, slightly downfield shifted. Okay, this is a quick summary of a proton NMR. This is something we are going to handle every chapter with the new molecules we encounter. Okay, let's summarize. Simple alkyl, 1 to 2. Heteroatom, around 3. Double bond, around 5. Aromatic ring, around 7 to 8. Okay, so with this, hopefully we can look at the proton NMR. Now, because of this, the movement of electrons, that movement is also imaginary movement. And if you take calculation or even crystal structure, looks like they are almost symmetric. Then, is that really this structure exists or not? Big question arises. Maybe in reality, it is evenly distributed, not double bond and single bond alternatively. When we counted conjugation system, this has a partial double bond character, right? Not strong double bond character. In benzene, this length is almost similar to 1.5 bond, is a half. And maybe this is a more realistic shape of benzenes rather than this kind of resonance structures. So based on this, we can make this kind of a molecular orbital. I said a molecular orbital. Let's review atomic orbital quickly. Atomic orbitals, if you think about this Schrödinger equation, now Schrödinger equation, when we solve, we assume there is a nucleus in the middle, and the electron is moving around outside here. This is our model of atom. Let me ask you, nucleus. What is the size of a nucleus? Nobody knows. Nucleus size. One femtometer. What is a femto? We learned pico. We learned nano. What is next? Nano is a 10 to the minus 9, right? Pico is a 10 to the minus 12. Bigger than nano, 10 to the minus 6. What is it?
Micro.
Micro. 10 to the minus 3.
Milli.
Milli. Okay, this is the unit we use for small units. Going up, kilo, giga, kilo, mega, giga, tera. That's the bigger direction, right? It's 1,000 times bigger. Smaller one, 10 to the minus 3, milli, micro, nano, pico, femto. Femto is minus 10 to the minus 15. Today we said carbon-carbon bond length is approximately 0.15 nanometer. Then this one is also approximately, we can think, 0.1 nanometer. 0.1 nanometer and 1 femtometer. How many fold? 100-fold? 1,000-fold? It's 100,000-fold. 10만 배. That means approximately we can think that this is size of atoms. Size of atom is approximately maybe 1 angstrom, 1 bond length. Nucleus size is smaller hundreds of thousand times. That means if you count only nucleus as material, nucleus has 10,000 times heavier material than electron. And we have a habit to think that nucleus is much bigger and electron is much smaller. But actually, nucleus position is out of one big playground. That's one ball size in there. The other space is a totally empty space. But we have the feeling of a volume like this. This is a feeling of a volume coming from electrons. Electron is lighter, but it is moving like wave like this. And that describes the nature of a material much better than the conventional model of Rutherford model. That's why we use this quantum mechanical model. And this volume, the volume filling of the material is electrons filling. 솜사탕이지만 우리가 느끼는 이 볼륨감은 전자가 만들어내는 볼륨감입니다. 핵이 차지하는 자리는 너무너무 작아요. 그렇기 때문에 우리가 다룰 때 슈레딩거 방정식에서 다루는 이 대상은 슈레딩거 방정식이 뭐 이렇게 표현되는데 기억하고 있는 사람도 있고 못하는 사람도 있겠지만 슈레딩거 방정식을 간단하게 쓰면 We make a model of electron. We assume that electron is kind of a wave. And arbitrarily we make the model using sine and cosine, the function. And then we apply some kind of operator. We make model first. And then we apply some operator. Operator means we give some operation, we apply some operation to this model. And then we try to get some operator which can regenerate the original function like this. And then if we generate same function and one scalar value, this equation we call eigenfunctions, eigenequations. 조금 복잡하니까 한국말로 할게요. 이해를 한 사람들도 있겠지만 우리가 전자에 대한 모델을 만들 때 전자를 파동이라고 생각하고 파티클 인 어 박스 모델에서는 이 안에서 존재하는 실이라고 모델을 만들었죠. 기타 줄처럼 이런 모델을 만들어서 사인 펑션과 코사인 펑션을 만들어서 계산을 했고 여기에 바운드리 컨디션이라는 걸 줬습니다. 경계면 조건. 바운드리 컨디션은 이 자리는 끝나는 자리 두 개는 0이라야 된다. 여기에 중간값이 있을 수는 없다. 이다 고정했기 때문에. 비슷한 일을 전자에다가 하고 스피리컬 코디네이트에 가합니다. 중간에 핵이 있고 핵은 플러스 차지를 띠고 전자는 마이너스 차지를 띠고 있어서 거기에 해당하는 위치 에너지 값을 여기에 주고 나머지는 전자가 이런 파동을 이루면서 움직인다고 가정하고 모델을 만듭니다. 이 모델을 만들 때 수학적으로 반복되는 모델을 만들기 위해서 사인이나 코사인 펑션을 써가지고 모델을 만들고 거기다가 어떤 오퍼레이터를 가해봤을 때 이 원래 펑션이 사라져버리면 뭔가 연구를 하려고 흔들거나 에너지를 줬더니 모델이 깨져버린 거죠. 그러면 더 이상 모델을 연구할 수가 없습니다. 그런데 어떤 오퍼레이터를 가했는데 원래 펑션이 다시 나타났어요. 그러면 최소한 우리가 그 원래 모델을 깨지는 않았다라고 생각할 수 있는 거죠. 그리고 어떤 주어진 상수값을 가지고 나타났습니다. 그러면 이 모델은 이 모델에 이 오퍼레이터는 적용해도 괜찮은 오퍼레이터라고 생각할 수 있는 거죠. 이렇게 푼 방정식이 슈레딩거 방정식입니다. 그 결과로 우리가 얻을 수 있는 것은 그럼 이 모델은 의미가 있는 모델이네. 제법 쓸모가 있는 모델이겠어. 이 모델이 보여주는 이 모델에서 나온 두 가지가 하나는 아이겐밸류라고 부르는 이 값은 나중에 분석하고 보니까 이거는 각 스테이트에서의 에너지 상태를 나타내는구나. 에너지 값을 주는구나. 이게 아이겐밸류고 여기서 얻은 이 아이겐 펑션은 따지고 봤더니 그 모양을 들여다봤더니 전자가 존재하는 확률로 설명이 되는구나. 제곱했을 때. 그 확률의 모양을 봤을 때 첫 번째 상태는 S 오비탈, P 오비탈, D 오비탈 하는 형식으로 여러 가지 상태를 가질 수가 있구나. 에너지가 여러 가지 상태로 퀀터아이즈 되어 있는 형태로 다시 말해서 연결되지 않고 각각 분리되어 있는 상태로 이렇게 존재한다고 가정할 수 있겠구나. 여기서부터 이렇게 계산을 한 결과에서 나온 거는 이거는 순수한 전자 하나와 핵 하나를 가지고 계산한 이 모델에서는 이 계산이 완벽하게 실험치하고 일치를 해요. 그 실험치라고 부르는 거는 태양에서 나오는 빛을 봤을 때 거기서 나오는 빛들을 우리가 확인한 이 빛들의 에너지가 계산해서 얻어낸 이 에너지 값들하고 너무 잘 맞아요. 너무나 아름다운 식인 거죠. 그렇기 때문에 이 일렉트론들은 이런 에너지 상태를 가질 수 있고 여기는 다 채워놨지만 실제로는 하이드로전 같으면 여기 전자가 하나밖에 없죠. 하나 있었던 게 이 전자는 비록 채워지진 않았지만 이 에너지 상태들은 원래부터 존재해요. 언제 존재하냐고요? 핵하고 같이 붙어있는 이 모델 요 안에서는 이 껍데기들이 다 존재해. 그리고 이 사이들을 왔다 갔다 할 수 있어요. 올라갈 때는 빛을 흡수해야 되고 내려올 때는 빛을 내놓습니다. 그게 실험적으로 확인된 것이 이 에너지 값들이고요. 이 값들을 이용해 가지고 모양을 유추했을 때 여기서 나온 이 모양들은 수학적인 해에서 얻어진 모양입니다. 슈레딩거 방정식을 풀었을 때, 웨이브 펑션을 풀었을 때 이 모양들이 나중에 아토믹 오비탈이라고 가정하고 모양을 만들었더니 굉장히 잘 맞았고요. 자, 이것들을 활용해서 utilizing these informations. If you go to benzene ring, now we can this individual one over here, this we can call this is atomic orbital. Now by combining those together and then making up linear recombination. 이것들이 각각 존재하는 하나씩의 일렉트론이라고 가정하고 각각이 콤비네이션을 만들 수 있다고 가정했을 때 we start with 6 atomic electron, then we can generate 6 combined, recombined molecular orbital. Originally we had 6 electron, we started to fill up those 6 of them. 자, 제가 앞에서 얘기했을 때 슈레딩거 방정식은 전자 하나에 대해서는 굉장히 잘 풀립니다. 전자가 하나 있고 핵이 하나 있고 전자가 하나 있는 모델로 만들었을 때는 너무나 아름다운 해를 주고 실험치하고 너무나 잘 맞아요. 이렇게. 그런데 핵이 두 개면 그래도 풀려요. 전자는 이 두 개 사이를 좀 복잡한 모션을 하지만 이렇게 돌아다닌다고 가정하면 되니까. 그런데 전자가 두 개가 되면 이제는 움직이는 아버지 핵이 두 개가 돼요. 핵이 두 개일 때는 핵은 전자가 움직이는 동안 거의 위치를 바꾸지 않는다고 가정하고 풀어도 별 문제가 없는데 전자가 두 개가 되면 한 전자의 움직임이 다른 전자에 미치는 영향이 거의 실시간으로 일어나기 때문에 이제는 전자 두 개를 놓고는 완벽한 해를 풀기가 어려워집니다. 그러면 가정을 써야 되고 근사를 써야 되고 얘가 움직이는 동안 얘는 움직이지 않았어 라고 가정하고 조금 움직인 다음에 나온 해를 놓고 그럼 얘는 여기 있다고 가정하고 얘의 움직임을 다시 또 기술합니다. 상당히 복잡하겠죠. 이런 방법으로 해서 풀어야 되기 때문에 근사가 들어갈 수밖에는 없어요. 그렇기 때문에 몰레큘러 오비탈은 슈레딩거 방정식에서 얻어낸 아토믹 오비탈로 근사치로 보태는 것이지 그걸 슈레딩거 방정식을 바로 그대로 풀기는 몹시 어렵거나 불가능합니다. 오케이? 자, 다시 영어로 돌아가서 We have learned about the structure of a benzene. Benzene has a very special character of stability. And all we know about the benzene ring is it's a cyclic. And it's a connected conjugation. Then how about this structure? Rather than 6-membered ring, this is a 4-membered ring, cyclic, but it's fully conjugated. Very interestingly, this molecule is not stable. This is unstable, not like a benzene. How about the 8-membered ring? 8-membered ring is also not stable. And looks like it's not planar structure. It has a little twisted structure. Then people think about what is the special thing for the benzene. Benzene is extra stable. And if you draw this kind of the molecular orbital, one trick here is you draw those cyclic structure one point on the bottom, 꼭지점을 바닥에다가 두었을 때 each point has a molecular orbital, you can assume. Then that is matching with this. Right? And then draw those half line. If the electron can be filled below this half line, then this molecule is stable. More stabilized than atomic orbitals, average of atomic orbitals, right? So that's why benzene is stable. What are you saying? Let's try with a 4-membered ring. 4-membered ring, we can draw this way. Then each 꼭지점, we have this 4 molecular orbital. If you fill up to those electrons, how many electrons here? 4 electrons, right? Then 1, 2, 1, 1. Now comparing to this average values, this much stabilized, but this one is not stabilized, right? The stabilization effect, not like benzene. Benzene is stabilized this much. This 4-membered ring was not fully stabilized. So by combining all of this, they tried to define the property of aromaticity. This aromaticity is not smelly property. Chemically speaking, aromaticity is unusual stability discovered in benzene. That's aromaticity. Several conditions. One condition, the molecule should be cyclic. Okay, makes sense, right? And then the structure should be planar. Means all the pi electrons should be on the same plane. This condition is the same condition for conjugation. Okay, if one molecule have a conjugated effect, all pi electrons should be on the same plane. If they are off the plane, then it's not conjugated. To be conjugated, the pi electron should be on the same plane and they should move around freely. That is the condition. Third one, they should be completely conjugated, means there should not be any broken structure. They should be, conjugation should be fully closed. Okay, this one is broken here, this one is broken here, right? In addition to this, now Quickel's rule come in here. If total pi electron number is 4n plus 2, they are stable. They are aromatic. Basic condition, they should be cyclic, planar, fully conjugated, and they require this number, then they are aromatic, means extra stable. And ring current happens there. If the electron number is 4n, then they are not stable, even unstable. So this property they call anti-aromatic. Okay. Benzene ring, 4n plus 2. If you put 1 here, that's a 6, right? This is aromatic. Cyclobutadiene, it's a 4n. It's an anti-aromatic. It's not stable. Benzene, if you mix benzene with another benzene, they are stable. They don't react. Butadiene with another butadiene, and then they react with this one with diene here, and then form this kind of a product. So if you look at only this part, this generates the product of this. Oh, sorry, product of this. This reaction, do you remember? This reaction is Diels-Alder reaction, right? We have learned last time. So butadiene is not stable, right? And now let's count this one. How many pi electrons here? Is this aromatic or not? How many pi electrons here? 야, 노트 보고 커닝하고 싶진 않은가 봐. 좋아. Here is a 14. 14 means 4n plus 2. 18. 18 is also 4n plus 2. So both of them are aromatic. How do you know whether this is really aromatic or not? If it is aromatic, we said there is a ring current happens, right? Ring current happens like this. If ring current happens, then what happens? Outside proton will be de-shielded. It goes to downfield in NMR. Inside here, it may be upfield shift. Benzene does not have the inside the proton, so that's why we didn't see that. But in this aniline, 18 aniline, we can see that. Inside, -3 ppm. Delta is the ppm are the unit. And outside is a 9 ppm. That's even downfield than benzene. Means there is a strong ring current happening here. And then this is downfield shift. This is the upfield shift. This is the evidence of ring current. And this is the evidence of aromaticity. Okay. So to summarize, aromaticity is a very unique stability phenomena in cyclic structure, benzene-like structures. They are aromatic and they are super stable, extra stable, and they have a very interesting ring current phenomena. Okay, there are many examples of this aromaticity. So next week, next class, till Thursday, we'll meet, and then no assignment by the time, and then we are going to continue this aromatic property. So we will look at different examples of aromaticity, and then we will check those the concept and also practice with the aromaticity decision. Okay, so this is the end of today's class. Any question for today's class? 질문 없어?
교수님, 저 질문 있습니다.
네, 질문하세요.
그 아로마티스티를 분배할 때 마지막 기준이 4n 플러스 2의 그 파일 일렉트론스가 있어야 한다고 하셨는데, 그래서 n이 어떤 걸 의미하시는 건가요?
Any defined like this. N can be either any kind of a 정수 like this. 0, 1, 2, 3.
그러면 그 n이 정수일 때 4n 플러스 2의 파일 일렉트론스만 가지면 되는 건가요?
In principle, following this rule. We will see the real example next time. So you will check whether this is always working or not.
네, 감사합니다.
더 쉬운 방법이 있는데, if you divide this into 2, 그러면 4n 플러스 2일 때는 홀수가 되고 4n일 때는 짝수가 되겠지. 2n 플러스 1, 2n 플러스 2n이 되니까. 그러면 더 쉬운 방법은 컨주게이션이 되어 있는 더블 반드 개수를 세봤을 때 홀수면 아로마틱, 짝수면 엔타이 아로마틱. 이게 조금 더 쉬운 방법이겠죠. 자, 자세한 예는 다음 시간에 여러 가지 실질적인 예를 가지고 아로마티스를 따져보겠습니다. 그래서 어떤 분자를 던져줬을 때 이 분자는 아로마틱 할까요? 아닐까요? 그런 걸 따져보겠습니다. 자, 다른 퀘스천? 자, 더 없으면 오늘 수업은 여기서 마치고요. 이번 주에는 숙제 없고 아까 내가 아침에 체크를 했을 때 숙제 2사람 안 냈던데 혹시 숙제 안 낸 사람 있으면 숙제 내주세요. 시간 맞춰가지고. 오케이. Last chance. Any question? 2분 남았어. 자, 질문 없으면 수업 여기서 마치도록 하겠습니다. 수고하셨습니다.
감사합니다.
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 교수님, 그 오늘 그 강의하신 자료는 수업 끝나고